All right, today we are diving into one of the most powerful, truly powerful, ideas in all of linear algebra. It's a way to look past all the numbers in a matrix and see what it's really doing. We're talking about eigenvectors and eigenvalues, the secret language of transformations. So let's just jump right in with a challenge, okay? Imagine someone hands you a matrix and says, calculate this to the 100th power by hand. It sounds like an absolute nightmare, right? Just endless, tedious multiplication? Think about it. Multiplying this matrix by itself 99 times, that would be a massive, error-prone computation. But what if I told you there's an elegant secret that makes this problem, well, almost trivial? A kind of mathematical shortcut that gets to the very essence of this matrix. That secret? It's all about eigenvalues. So here's our game plan for this explainer. We're going to start by uncovering the secret directions that are hidden inside every single matrix. Then we'll figure out how to find the magic numbers that define them. After that, we'll unleash the true power of this idea to solve that impossible problem. And finally, we'll see how this whole concept shapes the world around us. Okay, so to get our heads around this shortcut, we have to start looking at matrices a little differently. See, a matrix isn't just some boring grid of numbers. It's an action. It's a transformation. And you know how a piece of wood has a grain, a direction where it's easy to split? Well, every matrix has these special hidden directions where its action becomes beautifully simple.
Think of it like this. When you apply a matrix to most vectors, they get knocked around, sent flying off in some completely new direction. But there are a few special vectors, and we call these eigenvectors, that are different. They are perfectly aligned with the matrix's grain. They stay on their path. The transformation doesn't change their direction at all. It only stretches or shrinks them.
And that brings us to the official terms. The eigenvector is that special direction that stays the same, and the eigenvalue, that's represented by the Greek letter lambda, is simply the scaling factor. It's the number that tells us exactly how much that eigenvector got stretched, or maybe shrunk, or even flipped around. And this is it. It all boils down to this one single beautiful equation. AX equals lambda x. This is the whole key. It says that for these special eigenvectors, the complicated mess of matrix multiplication on the left side becomes nothing more than simple scaling by a number on the right. All that complexity just melts away. Okay, this is amazing, right? But how in the world do we actually find these magic directions and their scaling factors for any old matrix you give us? Well, it turns out there's a really clever, systematic way to hunt them down. So the trick is to rearrange our main equation a little bit. We are looking for a special number, lambda, that makes the matrix, A minus lambda I, do something really specific. It has to be able to take a non-zero vector and completely crush it down to zero. For a matrix to be able to do that, it has to be singular, which is just a fancy way of saying it collapses space in some way. And the mathematical test for a singular matrix? Its determinant has to be zero. So finding them is a super clear three-step process. First, you set up this characteristic equation. It looks a little scary, but it's straightforward. Second, you solve that equation for lambda. The answers you get are your eigenvalues. And third, you take each eigenvalue you found, plug it back in, and solve for its corresponding eigenvector. And here's a perfect example of that process in action. We take our matrix, we subtract lambda from the diagonal elements, then we calculate the determinant. That gives us a simple polynomial. We set that polynomial to 0, we solve for the roots, and bam, out pop our two magic numbers, our eigenvalues, in this case, 0 and 5. Now for the final step. We just plug each of those eigenvalues back into our system. For lambda equals 0, we find its eigenvector is any multiple of the vector 2, negative 1. For lambda equals 5, we find its partner eigenvector is any multiple of 1, 2. And just like that, we've found them. We've uncovered the hidden directions and the secret scaling factors for this matrix. Okay, we have the tools, we know how to find these things. So now let's circle all the way back to that impossible problem from the beginning and see how this new knowledge just completely demolishes it. And here is the absolutely beautiful leap in logic. This is the whole magic trick. If applying the matrix once is the same as just multiplying by lambda, then applying it 100 times is the same as just multiplying by lambda to the power of 100. That horrible, repetitive matrix multiplication just transformed into simple, clean exponentiation. What an incredible shortcut. So let's go back to that very first matrix from our challenge. It turns out its eigenvalues are 1 and 0.5. Now what does that mean? It means any vector you start with is really a mix of two different components. One component, the one that points along the first eigenvector, has an eigenvalue of 1. We call that the steady state. It never changes, no matter how many times you apply the matrix. The other component has an eigenvalue of 0.5, so we call that a decaying mode. It literally gets cut in half with every single step.
So what happens after 100 steps? Well, that decaying part, which is 0.5 to the 100th power, is so tiny it's practically zero. It's vanished. All that's left is the steady state part. So the columns of the matrix all converge on that first eigenvector, which happens to be 0.6, 0.4. And just like that, a problem that seemed impossible is now incredibly simple.
You know, what's really cool is that eigenvalues basically reveal the fundamental personality of a matrix. It's like finding its DNA. A projection matrix, one that flattens things, it's going to have eigenvalues of 1 and 0. A reflection, 1 and -1. A matrix that can't be inverted, it will always have at least one eigenvalue of 0. They tell you exactly what the matrix does at its core.
Now you might be thinking, okay, this is a pretty neat math trick, but I have to tell you, this concept is absolutely fundamental. It forms the bedrock of so many of our most important modern technologies. I mean, the PageRank algorithm that powers Google, it's all about finding the steady state eigenvector of a gigantic matrix that represents the entire web. Engineers use these to find the natural vibrating frequencies of a bridge to make sure it doesn't collapse. They describe the fundamental energy levels of atoms in quantum mechanics. And in data science, they help us find the most important patterns hidden in enormous datasets. It's everywhere. And as our source material puts it so perfectly, this whole thing isn't just about calculation. It's about perception. Eigenvalues give us an entirely new way to see into the very heart of a matrix, to truly understand its core function and predict what it's going to do in the long run. So the next time you see some complex systems settle down into a stable state, whether it's an ecosystem or the stock market or even just your search results, you can ask yourself, what are its hidden eigenvectors and what is its steady state eigenvalue at work? It's a powerful new lens for seeing the world. Thanks for tuning in.